Recording. All right, so any questions? So for those of you who are going to be doing 224 in fall, I'm going to break out some online collaboration tools that I wrote a number of years ago to allow people to interact during class. And I wasn't able to get them to work in the STEM building because the internet was too slow. But since we're going to be online in fall, I'm going to break those out, and hopefully it'll be a chance for people to participate and answer questions and things like that. So we won't have the silent screen of doom that we get sometimes. But anyway, that's something we'll talk about in fall if you're going on to the 224 sequence. All right, so question number 10 on the homework. Yes, let's take a look at that. So this is the access bit business. So question 10 asks, what would the access bit be in calling a clearF instruction on the following 12-bit file registers? So so these are locations in our data memory, right? And we've said a few times now, our data memory only has 256 general purpose locations that we can access. And we address these between 00 and FF. But if we think of these as 12-bit numbers, this is actually 3 zeros going up to hex 0FF. These are the general purpose registers. Those are the ones we set up as temporary variables we can read and write and so on and so forth. But then there's these special function registers, and these occur at the very other end of our 12-bit 4096 memory block. So they go from location F80 through FFF. And so this question is asking you to pretend that you're the assembler. You're being given an instruction which says, for example, clear file register F80, and it's asking you how would you code that up in binary. So we can start with the clearF opcode, right? So it's the same opcode through the entire problem. So clearF is a 0110. I'm going to write these down and then switch over to my camera. 0110 101A, and then 8 bits of file register. So clearF 0110 101A. Right. So the question is basically, what do we fill in for the access bit, and what do we fill in for those 8 bits of file information? So suppose we want to clear file register 0. All right, so the opcode's always the same, 0110 and the 12-bit address we're trying to clear is 0. So it looks like this, which means these low 8 bits which fill in the file part of the operand, those are just going to be zeros. And in fact, for each of these questions, those low 8 bits are going to be 00, 44, 84, FF, 80, FF, C0, FC, C0. This upper nibble, these upper 4 bits, doesn't affect what goes in those lower 8 bits of the instruction. So this is always easy to fill in, right? This is just going to be those 2 least significant hex digits. And the only real mystery is, what is the access bit? Okay, so the deal with the access bit is, if this is a 1, we use the bank select register, which for us is always 0, which means this is the address, right? So we 0 extend this 12-bit, this 8-bit operand. If this is a 0, we use what's called the access bank, which means we want to sign extend this 8-bit operand. All right, so 0, 0, 0, 0, 0, 0, 0, 0, right? Whether we extend that with zeros on the end or we extend it with the most significant bit, which is our sign extension, we're still going to end up with 12 zeros. So for this first question, we could use a 0 or we could use a 1. Makes no difference, right? Either will work perfectly fine. For the second question, we're trying to clear file register 44. Well, there the address looks like this. And we want those upper 4 bits to be 0. And again, if we 0 extend this, we're going to end up with zeros. If we sign extend this 8-bit number, we're going to end up with zeros. So A makes no difference in that case either. And you're seeing a pattern now, right? If this number is something smaller than 80 hex, that most significant bit's going to be 0. We can sign extend, we can 0 extend, we get the same thing. So the A bit does not matter if that most significant bit is 0. Well, let's look at this third case. We want to clear file register 84 hex. So we're trying to clear 084. Well, this is going to be our value of F. That's going to go in these 8 bits of our instruction. But we want the upper 8 bits to be 0. Now, if we 0 extend this number, we're going to get 4 zeros, and then an 8, and then a 4. So using A equals 1 is certainly going to work. If we were to make A equal to 0, what address would we be trying to clear? If A is 0, we're going to sign extend this, which means that's going to be the 12-bit operand we're working on, which is going to be hex F84. And that's not what we want. So for this case, the access bit has to be 1. And that's basically all there is to dealing with the access bit. So we're trying to do something on a 12-bit address, right, which if we write it with only 8 bits, there's zeros to the left. So we're trying to do something on a 12-bit address. We can specify the lower 8 bits in the instruction. If we need to sign extend this number to get the correct upper 8 bits, set the A bit to a 0. If we need to 0 extend this to get the upper 4 bits correct, set the A bit to 1. And if it doesn't matter, set the A bit to whatever you want. And the reason we spend time talking about the access bit is not because we need to set it up, right? Unless we're on a desert island and MPLAB doesn't work and we have to assemble the stuff by hand. We don't really need to understand this to write code. But it's very typical of the kinds of things we need to do on the PIC processor and on other processors to make it do what we want, right? So I want people to be thinking about these low-level, bit-level interactions. I want people to be thinking about understanding the architecture of this machine and figuring out how to manipulate that architecture to do whatever it is they want. Let's see, questions. So sign extend only changes 1s to 0s. Sign extend copies the most significant bit to the left. It's a general notion that has nothing to do with access bits per se. If you have an n-bit number and you want to extend it to more bits, take the most significant bit and just copy that out. Let's see, another question. Has anyone ever written a full program in machine code? Yeah, absolutely. So this was the first microprocessor that I worked on, and it is every bit as cool as it looks in this picture. There was no assembler for this. There was no keyboard for this, right? You had these paddles, and you could basically specify an address by flipping these 8 switches up and down. You could specify a piece of data by switching these up and down. And then one of these buttons would load that piece of data into that address. And so you would take the program you wanted, you would write it in your own assembly language, you would convert it into 1s and 0s by hand, and then you would go to the front panel and you'd put in a 0 on the address, put in the first 8 bits, flip the load button, change the address to 1, put in the new value for that, flip the load button. That's how you loaded your program in. And then when you were done, you could hit a button that said run, and it would start executing. And this was the coolest machine in the world, because I had never seen anything like it before. So yeah, before assembly language, everything was written in machine code. But one of the first things that people wrote in machine code was an assembler. So you could type your program up on, say, paper tape or Hollerith cards, and load that in and then have it be assembled. All right, cool. Other questions? So I graded the following questions. I graded question 18, which was looking at setting up port A to do input and output. So keep this in mind. When you want to read from pins, that's called an input operation. When you want to write to a pin, that's an output operation. And this can be ambiguous because it depends if you're looking at this from the point of view of the processor or the outside world. So I will be as consistent as possible. When you want to read from a pin, that's called input, and the corresponding bit in whatever tris register you want should be a 1. When you want to write to a pin, that's an output, and the corresponding tris bit should be a 0. So it's from the perspective of the processor. The processor is reading, the processor is doing an input operation. So 18 was about setting up the tris register and also setting up the ADCON register. You always have to set up ADCON 1 if you're doing digital I/O. The examples in the labs and in the textbook always do this clear file register on a port in the beginning of the program. There's no harm in doing that. And a lot of people like to do this in the beginning of the program so that they understand that, for example, all of the output pins are outputting zeros. It puts them in a known state. But there's no reason you have to do this. Okay? And in particular, you definitely do not want to do this except maybe once in the very beginning of the program. You don't want to do this in the middle of your program. For example, when you're adding two numbers and outputting the sum to a port, like in lab 2, don't clear that port before you output, right? Because if you hook that up to LEDs, what would happen? All your LEDs would go off briefly and then they would turn on and you would see the sum. And if this was feeding some other system, it would think the sum was 0 for a little bit. So you can do this in the beginning. It's a little bit like a dog turning in a circle 3 times before it sleeps. It makes people feel good. It puts things in a known state, but it's not necessary, right? And it's definitely not magic. And it's not something that we do for any particular reason other than, you know, if we're just starting the program, let's put all the outputs to a 0, just so we know what the value is. All right, so I'm going to go back and talk a little more about tris A, tris B in a moment. So I looked at 18 and 23. So 23 we were reading from pins 8 and 9, which if you look at the data sheet correspond to RB0 and 1. So we read those from port B. You have to set up tris B to make those 2 pins input pins. You have to set up ADCON 1. And then you can move from port B into the W register. But question 3 here asks, is the W register exactly the same as that 2-bit number? And the answer is no. Okay, so let's try this. Suppose you have a parking lot. Remember when we used to drive places in cars? We have a parking lot. There's 8 parking spots. And there might be a car present in one of these, and there might be a car present over here, and you know, there might not be a car in the other spots. That's either a bug or a car. And suppose you want to know, are these 2 spots empty? Right? Because you want to know if somebody is home, and this is the parking spot for the 2 people who live there. So you want to know, are these 2 spots empty? Okay, so this is all hooked up to a microprocessor, and you can read from, say, port B. And when you read from port B, you get 1s and 0s telling you whether there's a car in each spot. So I'll set up port B and I'll say let's read from these two locations, and I'll copy it into my W-reg. What is my W-reg going to be equal to? 01010000. Right? That tells me more than just are these two spots empty, right? To know if there's any cars in here, what I'd like to do is say, you know, is this equal to 00? But I can't just read port B and say, is port B equal to 00? No, it's not. I guess those spots aren't empty, right? That doesn't work, because when I read from port B, yeah, I have information telling me if those two spots are empty, but I have all of this other stuff in there too. And if you read from port B and then try to, you know, treat that as a 2-bit number, 2 of your bits are correct, but your other 6 bits, who knows? Probably not correct. So the third part of this question was to mask off some of your bits. In other words, do an AND. If this is in the W register, you can AND it with the literal, consisting of 6 zeros and 2 ones. And that's going to force these upper bits to be zeros. And now my W-reg would look like that. And now I can say, is this equal to 0? If it is, then these two spots are empty. If this is not 0, then at least one of these spots is occupied. So it's just throwing away some of the bits, basically, turning them into zeros. So that was the point of question 23, and we talked about that last week too. Question 29, write an assembly language program keeps incrementing register 80. So not a lot of problems with this, right? Increment file register 80 and then branch back. So a few ways to do that. Right, increment file register 80 and then go to loop. This is a label, LOOP colon. Does not generate any code. It's not an instruction. Okay, it's telling the assembler, it's a directive, it's telling the assembler, if I talk about loop later on, what I mean is the address of this instruction that comes after that label. You could also say branch to loop, and that works just as well. You don't want to clear file register 80 though, right? It's not asking you to write code that clears file register 80. It's just asking you to keep incrementing file register 80. Unless the instructions you're following say something like clear the file register or clear the port or something like that, don't ever do anything that's not asked for. Okay? If you're writing an entire program yourself, you get to do things like, you know, include directives and set up ADCON1 and all that kind of stuff. But when you're asked to just write you know, something that increments a location or adds 2 locations, don't change those locations. Okay, don't take it upon yourself to initialize them or put them in a loop or something like that. Alright, 30, same thing, increment 80 and 82, decrement 81 and 83, that's 4 instructions and then a branch or a go to. Shortest infinite loop that you can write is either something like this, loop, go to loop, or loop, branch loop. Each of these is a single instruction. This instruction happens to take 16 times 2, 32 bits. This one only takes 16 bits. So in terms of memory, this one is actually smaller. But they're both a single instruction. So in terms of number of instructions, they're both equally short. But that's the tightest loop you can make. And it just jumps to itself. And you'll find this code inside a lot of programs. There's lots of cases where you actually want a very small infinite loop that doesn't do anything except loop forever. We'll be using these a lot in the upcoming labs, starting with lab 3. Alright, so those are the questions I graded. 10 questions, 2 points each. And I tried to give you feedback if there were any deductions. Let me talk once more about Tris A, and this is not so much just because of Tris A, but it's because what we're going to be doing is dealing with hardware inside the PIC processor And the way we deal with most of the hardware is going to be very similar to the way we deal with Tris A and Port A, which is taking an 8-bit register and interpreting each of the individual bits and manipulating those bits to do something in particular. Okay, so here's my final version of Tris A and Port A. Imagine there's a restaurant, and there's a dining area. So this is dining, and there's a kitchen, and there's a door. And people can go from the dining area to the kitchen, and people who are taking out food can go from the kitchen to the dining area. And what's the problem with... Sorry?
Oh, we can't see the...
Oh, there we go. Okay. There's my beautiful dining area and kitchen, and there's a door. Okay? And the obvious Comic 101 problem with this is that somebody going into the kitchen will push the door at the same time someone's coming out with a plate of food, and you have a disaster. So typically you have 2 doors. And the understanding is one of these doors is for going in this direction, the other one is for going in that direction. Okay? This only works if everybody understands which door they're supposed to use. So we're going to label these doors, and for example, I'm going to say this is an input, and this is an output. So the door labeled in, you can use to go from the dining room into the kitchen. And the door labeled out, you can use to go from the kitchen into the dining room. And that works great, right? Anything going from the dining room to the kitchen goes through this door, and anything going in the other direction goes through that door. All right, now just imagine that we have 8 doors, and now you can have more traffic, okay? But you still need to indicate on each door whether this is for going in or going out. So maybe we'll set it up like this. There's 5 doors that can be used to go from the dining room to the kitchen. There's 3 doors that can go from the kitchen out into the dining room. All right? And these, are little signs that are hung on the doors. Well, what do these signs look like? There's a 1 or a 0. And these very smart people working in the restaurant understand 1 means that it's an in door, and so they can go into the kitchen, and so on and so forth. Okay? So 2 takeaways from this. 1, you want to figure out what signs to put on the doors in the very beginning of the day, right? The start of your program, or when your restaurant first opens its doors, right? You're not going to change these every time that an order comes up and somebody has to move from one room to another. These get set up in some kind of initialization. You decide for whatever reason these 3 doors are going to be for going in one direction, and these 5 doors will be for going in the other direction, and you hang up those signs on each of the 8 doors, and then you leave it alone, right? And now when you want to move in and out, you use the port register, right? You use the doors. The signs, which are, the tri-state registers, those are just indicators for is each of these doors, is each of these bits supposed to be used for reading in from a pin or writing out to a pin, input or output. Okay, it's a setup thing in the very beginning. The other takeaway is that unlike in real life where we could have 8 signs, for some reason in this restaurant you have a single sign with 8, things written on it. And you have to hang that 1 sign above all 8 doors with, in and out written on them. So if I decide, for example, that I want to change this to be an output, in general I can't just say set tris to be, a 0 over here, right? I need to specify all 8 bits. So I would need to go and say, okay, I want this to be 0, 1, 1, 1, 0, 0, 0, 1. And I would take that 8-bit pattern and I would dump it out to tris A or B, right? And now that's what each of these bits is designated to be. Output, 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 and then 4 inputs. All right, so that's a slightly different approach to tris and port. But this idea of individual bits in here corresponding to certain aspects of the hardware, right? This is going to be something we do the rest of our course. All right, so I want to make sure we've talked about that. All right, questions on that? Alright, I sent an announcement and I changed Canvas and I should have sent you an alert, but I'm postponing the midterm for a week. So the midterm will not be this Thursday, it'll be a week from Thursday. And as I mentioned in the announcement, the idea of that is that you've only gotten 2 homeworks back at this point. You'll only have gotten 1 lab back, possibly 2 by Thursday, but possibly not, and we'll only have talked about your first lab, and it's just not a lot of material to test you on. So I want to make sure we get through a 3rd batch of homework, okay, and a 2nd lab before we go ahead and do a midterm. So midterm will be end of week 5, which is a little late in an 8-week course, but I think it'll give us a better chance to sort of check where everybody is and course correct as necessary and be in good shape for the final and for whatever comes after 270 for you. So 1 week delay on the midterm. Hopefully doesn't ruin anybody's week.
Did you use the data sheet on the midterm?
So the midterm, you're allowed to use your notes. You're allowed to use the pick data sheet summary that's posted on Canvas, that 18-page summary, and that's it.
Okay.
Okay, I'd like you not to use online resources, and I would definitely like you not to use MP Lab. Okay, because if I ask you to assemble an instruction into machine code, right, you can just pop it into the assembler and do that. That defeats the point. And it should be in the in Canvas under the midterm section. It should repeat that. But I think that was the way I set it up. All right, questions about stacks or call and return. So let's talk a little more about stacky things. So let's write some test code. So there's another pair of instructions we can work with. These are called push and pop. So push and pop, they don't take any operands. They're just opcodes. So we can say push, we can say pop, and that's pretty much it. So let's see what these things do. I'm incrementing file register 80 a lot just because I want to get to some more interesting addresses in memory, but that may be making people think that we always need to increment. So I'm going to use no ops, and I'm just using these to not be writing at the beginning of my program. Let's do a push instruction. Let's do another no op or 2. Let's do another push. Let's do a pop. Let's do another pop. Let's do another pop. And let's end. So this is a questionably useful program. And I probably need to turn on debugging symbols. Alright, Alright, so I'm doing this so I can get debugging information. Let's build this, and let's look at our disassembly listing. Alright, it's a bunch of no-ops, a few pushes, a few pops. Let's go ahead and run this. And let's look at some variables. Let's look at the stack pointer. Let's look at top of stack low. And we'll just leave it at there for now. No, let's go ahead and look at the PC. I can get the PC up here on the top bar. PC is 0, but let's look at it down here in our variables too. So program counter is 0. We're about to execute this first instruction, which is no op. We execute that. Remember, most of our instructions take 2 locations, right? And no op, even though it does nothing, takes 16 bits to code. It's all zeros, which means our current instruction, the second no op, is at location 2. So it's about to execute the instruction at PC 2. We can execute that. Now the program counter is 4. That's the next instruction about to be executed. Let's execute that no op. Now we're about to execute a push instruction. The program counter is 6. That's the address of the push, right? Push right here. Address in memory is 6. The address of the instruction following the push is 8. So 8 is what's going to get pushed onto the stack. Okay? The push instruction pushes the address of the next instruction onto the stack. So if I execute this instruction, top of the stack is now equal to 8. And the stack pointer, which tells us how many things are on the stack, is equal to 1. And I can do a couple of more no-ops, and that doesn't change anything, but now I'm about to do another push. The program counter is C, which means the address of the next instruction is E, so when I say push, E is going to get pushed onto the stack. There's the top of the stack is an E, and the stack pointer is 2, saying there's 2 things on the stack. So pushes are used to push the address of the next instruction on the stack, but they don't actually jump anywhere. Now a call basically does a push followed by a goto. So a call says push the address of the next instruction on the stack and then go to the address it's specified by the argument of the call, the operand. So a push is like a call without actually a jump to anywhere. But it manipulates the stack the same way. Alright, so we can do a few more no-ops. And now we're about to execute a pop instruction. Okay, our program counter is 12 hex. Top of the stack is still E. Number of things on the stack is 2. What's going to happen after we say pop? It's going to pull that top dish off the stack of dishes. It's going to get rid of that E. And whatever was on there before, which I believe was an 8, will move up to the top of the stack. And stack pointer will change to 1, saying now there's only one thing on the stack. So there we go. Alright, so the stack is just something that we call a data structure. It's a separate area of memory, and we can do 2 things. Push something on the top of it or pop off whatever's on the top. And stack pointer tells us how many things are on the stack, and top of stack tells us the contents of the top of the stack. And if I do another pop, stack pointer goes to 0. And if I do another pop, that's an error condition. I'm saying tell me what's on the top of the stack, but the stack is considered to be empty. We pushed 2 things, we popped 2 things. There's no plates left in the pile of plates. So if we say give me another plate, that's an error condition. And in this case what the processor does is it resets. It goes back to program counter 0. And it sets this bit in the stack pointer register saying, hey, something went wrong. So the stack pointer looks like this. It's got 5 bits down here, which correspond to a number between 0 and 31. That's the number of things on the stack. This 6th bit is unused. This 7th bit is set to a 1 if a stack underflow occurs. That's what happens when you pop too many things. And the 8th bit is set to a 1 when a stack overflow occurs. That's what happens when you push too many things. So typically what you do in the beginning of your program, you check to see if either of these bits is set, and if it is, something went wrong. And it means an error occurred, the processor reset, and now you've got an overflow or an underflow. So question from someone: would we use the push to set something aside and save something to be popped later? In a normal system, in a non-PIC system, yes, that's exactly what we would do with a stack. On the PIC processor, it's yeah, you could do that with the PIC. You can read what's at the top of the stack. The problem is you can only push the address of the next instruction. So it's not as useful in general. Now you can fake it. You could push something to the top of the stack, and then you could manually change the stack value and use that as say temporary storage. But in another system, you know, a typical ARM system or an x86, yeah, the stack is used for general purpose storage for later retrieval. So for example, if we run this again, we push an 8 on the top of the stack. I could come in here and I could change this to, you know, 55 and save that on my stack. And now go ahead and push my E on the top of the stack. So I have 2 things on the stack, and the top of the stack is an E, but the thing below that is this 55 that I manually placed on the stack. And so when I say pop, I pop off the E. Oh, that 55 did not take. Interesting. That's either a MP lab glitch, or maybe you're not allowed to manipulate the top of the stack. Let me try that once more. There's my push instruction. So that's definitely a 55 on the top of the stack. And that's an E. Pop off the E. Yeah, okay, 55. I must have done something wrong last time. So yeah, we can use the stack as general purpose storage. The downside is it's a little funky to use, but mostly it's very limited. It's only 31 locations, and it's pretty easy to blow up. So there are homework questions. Let me see something. Let me see what I gave you. 32, 33. Determine the PC. 34 through 40 are conditional branch type questions. 43 through 48. Alright, so I did not give you these stack questions. Yeah, I'll give you those on Thursday. So if we want to visualize what a stack looks like, right, we can draw a pretty simple picture. So question 49, I'll give this to you on Thursday. Draw an abstract stack and perform the following operations. Push 10, push 20, pop, push 10, pop, pop, pop. Yeah, let's not talk about that. That's a bogus question. Okay, we'll come back to that Thursday. Questions about stacks so far? Pushes and pops, calls and returns. The main thing we care about with stacks is call and return. And the real reason we need this is if we want to do nested calls. If we have a set of code and we want to jump down and execute some other code and then come back and continue, right? That we could do with a set of branches. We could say at this point branch to my subroutine, and down here we could say branch back to my main program, right? The reason this doesn't always work is, for example, somewhere else in our program we may want to jump to that same subroutine and then return back to this other location. So we need to do a jump down here, but we need to say, hey, when you're done with this function, where should you go back to? Well, if I called you from here, I want you to go back here. If I called you from there, I want you to go back there. Right? So that's what a call does. It saves the address of the next instruction on the stack, and then the return statement says go back to the address that was on the top of the stack. So the thing that determines, this is a question, the thing that determines the value being pushed onto the top of the stack is the program counter, the location in program memory of the next instruction. So if I say push right here, wherever this instruction is stored in memory, that address is what gets pushed on the stack. And if I say something like call hex 120, right, supposing I've got some interesting code down at location 120, so I'm about to execute this call, the address of this no-op is what gets pushed on the stack. And if you look at our disassembly listing, the call is stored at location 2 in memory. The following no-op, which is down here, is stored at location 6 in memory. So when I execute this call, 6 is going to get pushed onto the top of the stack. Right, so top of the stack is 6, stack pointer is 1, saying there's one thing on there, and my program counter is AE for whatever reason, because I didn't have something defined at that location. Alright, so push and call always push the address of the next instruction in memory. If I take the same code but I started off at location hex 110 and I debug this, I'm about to execute a call statement. Well, look at your disassembly listing. That call statement is at location 112. The the following instruction is stored at location 116. So 116 hex should get pushed onto the top of the stack. All right. Well, there's a 16 hex. What happened to that 1? So top of the stack is actually 3 registers. There's a top of stack high, and there's a top of stack upper. Yeah, it didn't let me move them. So if we want to know what the top of the stack actually is, we have to look at 3 registers: top of stack upper, top of stack high, top of stack low. It's 8 zeros, 7 zeros, and a 1, 3 zeros and a 1, and then a 0, 1, 1, 0. So it's hex 116 on the top of the stack, which is what? Hex 116 is the address of the instruction following the call. And our program counter low is hex 20, but program counter is also a 3-bit register. There's a program counter low. There's a program counter high, which I'm apparently spelling wrong. And there's your program counter upper. I'm having trouble locating the program counter. Let's see where it's stored. Program counter low. I'm not sure I can read the whole program counter from here, but I can look at it up here on the top, right, and see my program counter is 120 hex. So that was the result of doing that call instruction. All right, other questions? All right, let's talk about timing. So I think we've glanced at this picture before. This is the clocking subsystem inside the PIC processor. Clocking is a whole discipline in itself. On a typical PC, there's a bunch of clocks, right? There's these crystals, these little tiny pieces of quartz that resonate at a certain frequency, and they're stimulated and used to deliver a very precise pulse. Just like a 555 timer, we can set it up to pulse every 2 seconds. You can get a crystal that will pulse every 500 millionth of a second. And these very precise signals are used to generate other timing signals. And in a typical computer, there's software registers that you can modify to control how fast your CPU is clocked. And if you play around with overclocking, that's really what you're doing, is adjusting these multipliers and dividers to take this base frequency and use it to generate different frequencies from what was originally intended by the manufacturer. So on the PIC processor, there's a similar system. There's an internal oscillator, but this one is not crystal controlled. Okay, this one is actually a pretty imprecise oscillator. And it's basically built with a little feedback loop. And it generates a roughly 8 megahertz signal, so 8 million ticks per second. And then we can divide that down to get slower signals coming out here on this internal oscillator line. No, the 555 does not have a crystal. It's what we call an RC circuit. So if you take a resistor and a capacitor and you hook them up in a pretty simple configuration and you analyze them, you start finding trigonometric terms in the solution of the voltage equations. And so they're oscillating. And by adjusting the capacitance and or resistance, you can change the rate of that. So the 555 really has inside it versions of that circuitry. But it's all what we call discrete logic, capacitors and resistors and transistors and things like that, but there's no crystal timing in there. So on a PIC processor, we can scale down that 8 megahertz clock to any of these lower frequencies, right? Or we can take a very slow internal RC and use that to generate our internal oscillator. And these are special function registers, oscillator configuration, or configuration bits. These are things that are set up under software. Okay, out of the box, if you don't do anything else, the base frequency of a PIC processor, a PIC 18F1220, is 31 kilohertz. And sometimes you see 32 kilohertz, because 32 is almost the same as 31, but it's easier to divide. But you know, roughly 31, 32 kilohertz coming out. Okay, and this is called the oscillator frequency. So 32,000 times a second. This thing is ticking. All right, so here's how instructions get executed. This is our oscillator frequency. Up and down, up and down, up and down, up and down. It takes 4 of these ticks to fetch one instruction from your program memory. It takes 4 ticks to do a fetch. This is a state machine. Remember your state machines from 250. Every time the clock ticks, you move to a new state. Through a succession of 4 states, the processor will take the program counter, send it to the program memory, put a 1 on the read pin to say read from this location, wait a little while for the memory to deliver those bits to the output pins, and then take those bits and load them into internal registers inside the PIC processor. It takes 4 clock cycles, at the end of which the instruction has been what we call fetched. And then another 4 instruction cycles are required to do the decoding and executing of the instruction. So one instruction actually takes 8 instruction cycles to execute. A typical instruction like increment file register 80. So 4 ticks to pull this instruction, the ones and zeros, out of memory. 4 ticks to say, hey, it wants to do an increment, read this location, modify it, write it back. Total of 8 ticks. With 32,000 ticks per second, it takes 8 of them to execute one instruction. That's approximately 4,000 instructions per second that the PIC processor can execute. Not terribly fast. 4,000 instructions per second. But life is a little better than that. So the subject here is pipelining. And pipelining is the key to kind of our world right now. To the degree to which our world is based on fast computing, pipelining is the key. All right, so here's the classic example of what pipelining is. Suppose you're doing laundry, okay? And here's what the laundromat looks like. You have a washing machine. You have a dryer. It's a front loader. You have a folding table. And you have a closet where you put your clothes away. Alright, 4 steps to doing a load of laundry. Wash them, dry them, fold them, store them. 4 steps, 4 stages. And suppose it takes 30 minutes for each stage. Your washer takes 30 minutes to wash, your dryer takes 30 minutes to dry. It takes you 30 minutes to fold a load of clothes, and the storage is, in another room. So it takes you 30 minutes to carry your clothes over and put them away. Okay, so one load is going to take you 2 hours. Okay, if you're kind of new to doing laundry and you have 5 loads of laundry to do, what might you do? You take the first load, you wash it, you dry it, you fold it, you store it. been 2 hours. Now you take the second load, you wash it, you dry it, you fold it, you store it. You've done 2 loads in 4 hours. Now you take the third load, you wash it, you dry it, you fold it, you store it. You've done 3 loads in 6 hours. Okay, so on average, it's taking you 2 hours to do a load of laundry. But that's inefficient, right? What's the more efficient way to do your 5 loads of laundry? What's the trick?
Can you combine the loads?
You can only do 1 load at a time. You can only wash 1 load at a time. You can only dry 1 load at a time.
You could wash right after 1 load finishes.
Mm-hmm. All right. So we're going to put our first load in here. And after 30 minutes, we're going to put our first load in the dryer, and we're immediately going to put our second load in the wash. And after 30 more minutes, we'll start folding our first load, but we'll put our second load in the dryer, and we'll put our third load in the wash. And after 30 more minutes, we'll start storing our first load, folding our second load, because we can multitask that way, drying our third load, and washing our fourth load. Okay, so after 2 hours, we will have finished storing 1 load of clothes. But something magic happens. 30 minutes later, we're storing our second load of laundry, we're folding our third, we're drying our fourth, and we're already washing our fifth. And after 2.5 hours, we will have finished 2 loads of laundry. Well, right now, the time to do a load of laundry just dropped from 2 hours to 1 hour and 15 minutes, because we just did 2 loads in 2.5 hours. All right, 30 minutes later, we start storing our third load, folding our fourth load, drying our fifth load, and our washer is empty. And so after 3 hours, we've done 3 loads of laundry. Well, now we're down to only 1 hour per load. We've doubled our speed at doing laundry. Instead of 2 hours a load, it's only 1. And so on. Now, after we've washed our fifth load, the washer is empty. After we've dried our fifth load, the dryer will be empty, and so on. Our pipeline is emptying out, but while our pipeline is full, what's happening? Every half hour, we finish another load of laundry. So our average throughput is 30 minutes per load. That's 4 times faster. That's phenomenal. And we didn't need to invent a faster washing machine or a faster drying machine. We just needed to pipeline these things. So pipelined architectures rule the world right now. It's the reason that ARM is the most commonly used architecture out there, is because it supports this pipelining. Now this pipeline had 4 stages to it. That's why we got a 4x speed up, from 2 hours down to a half an hour. If we had broken this up into 10 stages, theoretically we can get a 10 times speed up. Okay, a few things to keep in mind. Number 1, it's still taking 2 hours to do a load of laundry. If you come to me with a new load of laundry, I can't finish it in 30 minutes. It still takes 30, 60, 90, 2 hours to do a single load. But the throughput, right, how many loads we finish in a certain period of time, that's what's being increased. All right, so we're increasing the throughput, not the raw speed. That's one key point. The second key point is we need to be able to break our task into these independent pieces. So for example, if I'm the only person doing laundry, I really can't be folding clothes at the same time that I'm storing them. I can toss them in the wash and be done. I can toss them in the dryer and be done. But these 2 steps are hard to break up. unless I have more resources. So I get a friend and I say, hey, you want to help me do some laundry? And they're like, sure. So they come over and maybe they're folding clothes while I'm storing. Now we've got a nice efficient pipeline. But you may need more resources, or you may need to change the structure of your resources. Okay, so that's the second key part, is that you have to adapt your architecture to support this kind of pipeline. The third important aspect is what happens if sometimes you're drying clothes and the door opens a little bit and the dryer turns off, right? So you finish folding and storing, and you come back to put the wash into the dryer and the dryer into the folding, and you look and your clothes are still totally wet because something went wrong at this stage of the pipeline. Okay, you have to restart this. This is going to take another 30 minutes, and during that 30 minutes, the folding table is idle. The resource that's storing your clothes is idle. This is called a pipeline stall. And what happens is your throughput starts to go down, because 30 minutes later I'm not going to finish storing something, and 30 minutes after that I'm not going to finish storing the thing that I should have been folding right now. Everything from this point on goes on hold. There's another possibility. I'm working my pipeline, I'm happily grabbing another load, tossing it in here, moving things down, and so on and so forth, and at some point someone knocks on the laundry room door and says, hey dude, I think you got my laundry by mistake, and I realize I'm not washing the right clothes. This is what happens when you hit a conditional branch and you suddenly say, hey, I shouldn't be executing the next instruction in memory, I should be executing some instruction somewhere else in memory. Well, I started doing some drying, some folding, and some storing, and it's not the clothes that I want to be doing anymore. I have to flush my pipeline. So I clear out this station, I clear out the dryer, I clear out the washer, and I take the correct load of clothes, and I put the first load in the wash. And the dryer is idle, the folding and storing stations are idle, and for the next 2 hours, that first load is working its way through here. Okay, I've just had a pipeline stall. And I'm going to see this 2 hours before that first load pops out. Now after that, I'm back to every 30 minutes another load's going to come out. Okay, so these are all things that happen inside processors, and they critically affect the design of the processor, the design of the program, the design of the compilers and the assemblers, and everything else. And it's all about trying to have a long pipeline that you can use efficiently and trying to avoid having stalls where you have to change what's going through your pipeline and basically lose your pipelined output. Okay, and so someone asked, is this the idea behind multi-core processing? It's part of it. Multi-core processing is it's partially, at a higher level, being able to take a task and break it into pieces. So for example, you've got a video game and you've got 3 players, and each of them needs to have a physics engine calculating updates to their position. Well, maybe you can put each of those on a separate processor and calculate those things at the same time, because there's minimal interaction between them, right? So a multi-core system could take advantage of that. Pipelining is pretty low level. It's really, below the level of the machine language even. It's something happening pretty deep inside. But to some degree, things like compilers will take advantage of aspects of the pipeline to improve performance. Alright, so how does this work on the PIC processor? We have a 2-section pipeline. There's a fetch and an execute stage. And remember, we started off by saying that when you want to execute an instruction, it takes 4 cycles to do the fetch and 4 cycles to do the decode and execute. Well, it turns out that while you're fetching an instruction 1 from memory, you can be executing another instruction. So here's a typical pipeline. Here's a move instruction. You're fetching that move instruction from memory. There's nothing to execute yet. This is the first instruction of the program. So 4 clock cycles, you do your fetch. The next 4 cycles, you begin to execute that move, moving a 55 into W, but at the same time, you can fetch this next instruction from memory. Now we can't execute this instruction because what does this instruction 2 do? It moves the W register to port B, and we haven't loaded W with 55 yet. We have to finish executing 1 before we can execute 2, but we can absolutely fetch instruction 2 while we're executing instruction 1. And then as we begin to execute instruction 2, we can fetch instruction 3. So this PIC processor has a 2-stage pipeline. And it increases our throughput so that it basically takes 4 instruction cycles to do 1 instruction. Even though it takes 8, right? 4 to fetch, 4 to decode and execute. Even though it takes 8 instruction cycles to execute 1 instruction, the effect is once our pipeline is full, every 4 instruction cycles we complete another instruction. So it looks like 4 ticks per instruction. And that's the number we're going to work with when we're looking at instruction timing. So it's really 8 ticks, approximately 4,000 instructions per second. But because it's pipelined, it's basically 4 instruction cycles per instruction. And with a 31 kilohertz processor, it's approximately 8,000 instructions per second that we can complete. And so if you look at your data sheet and you look at the different instructions on there, you can see, for example, in add WF, how long does it take to execute 1 cycle? Clear file register takes 1 cycle. Negate file register takes 1 cycle. Okay, these are and I messed up my terminology on you. Let me not call this an instruction cycle. 4 clock cycles for 1 instruction. So 8,000 instructions per second. But there's an exceptional thing that can happen. And these topics we're talking about, by the way, this is the core of like an entire semester long graduate level course maybe on computer architecture. Okay, so we're talking about a lot of heavy stuff, and I just want you to kind of get a general feeling for it. I'm not going to ask you about precise details of this, but I want you to just kind of get a general overview of this. We're doing, execute 1 instruction while we're fetching the next instruction. So the effect is every 4 cycle, every one of these instruction cycles, we complete another instruction. Okay. Well, up here is a branch statement. This is saying let's branch somewhere else. And while we're executing instruction 2, which is the move WF, we are fetching the branch instruction. Okay. At this point, we start to execute the branch instruction, and we are pre-fetching the following instruction in memory, which is bit set file. We're not going to execute this instruction though, because the branch is going to take us somewhere else in memory. So we're executing the branch, we're figuring out, oh, this is a branch, it's going to change our program counter, and we're pre-fetching the wrong instruction. We should be pre-fetching the instruction at wherever sub 1 is, but we don't know that until we finish executing the branch. So we're executing the branch, we're fetching an instruction that we're not going to use. So for the next instruction cycle, we have a pipeline stall. And this next instruction cycle we're going to spend going back and fetching the correct instruction, which is the instruction at sub 1. And there's nothing to execute here, because the instruction we fetch, this bit set file instruction, we don't want to execute that because we branched somewhere else. So there's a pipeline stall. And so we executed instruction 1, next cycle instruction 2, and next cycle instruction 3. But to execute the next instruction, which was at sub 1, took us 2 instruction cycles. That's a stall. And if you look at the data sheet and you look at these branch instructions, you'll see that they take a branch itself takes 2 cycles. A conditional branch takes 1 or 2 cycles. We don't know, because it depends on whether the condition is satisfied or not. If we say branch shift 0 and we end up branching, it's going to take 2 cycles effectively to execute, because we're going to get a pipeline stall. If we say branch shift 0 and the branch is not taken, then the instruction that we had prefetched was the correct one and we continue with a full pipeline. Okay, the only thing I want you to take away from that is conditional branches are really hazardous to your pipeline. If you have a conditional branch and it's going to cause you to execute something other than the next instruction, you're going to end up flushing your pipeline. And on the PIC processor we're using, that cost us 1 more cycle. But on a sophisticated ARM processor with a 13-stage pipeline, we're going to see a 13x drop in speed for the next 12 instructions, while our empty pipeline, our pipeline that's been flushed, is slowly getting filled up again. These branches are brutal. And a lot of work has gone into dealing with this problem. How do you deal with the fact that there's a branch coming up? Well, if it's really just an unconditional branch, you can add more hardware to your system and detect, hey, there's a branch coming up, and have it not do this fetch from the next location in memory, but have it actually start fetching from sub 1 in this case. So you can start building something into your fetch logic that actually understands branch instructions. But what about conditional branches? You're going to say branch shift 0, and that's based on the result of a calculation that you haven't done yet. How do you know whether you're going to branch or not? If you can predict correctly, you can keep your pipeline full. If you predict incorrectly, you flush your pipeline, you get a stall. So there are circuits inside your processor that will try to predict whether a branch is going to be taken or not. And how is that done? Well, sometimes it's done with statistics. There's circuitry that keeps track of how many times you've branched, how many times you haven't branched, and uses that to try to predict the future. And the better a job you do at predicting the future, the faster your processor is. So this is a crazy world, okay? There are so many tricks and games and techniques that are used inside modern processors, all in the name of keeping this pipeline full. Most of which we don't have to worry about, okay? The timing that we're going to be concerned with in Lab 3 and forward is pretty rudimentary, okay? It's really just kind of looking at, you know, rough ballpark, how long is it going to take to execute some instructions. And mostly we'll just use the number of cycles from this table. In conditional branches, we can use 1 or 2. Doesn't really make a big difference. Unconditional branches we'll always use 2. Alright, so quick wrap up. Default 31 kilohertz oscillator, that's the system clock, translates into effectively roughly 8,000 instructions per second. Alright, let's take a 5-minute break. We'll come back and we'll look at how we can use this to control timing, and then we'll take a look at Lab 3, which is going to involve generating timing loops. Alright, it's a 5-minute break. We'll come back and we'll take a look at that.